Very good morning. We are continuing with principal component analysis. Today we discuss on extraction of principal components. We will also show one example related to this. Let's go to the next slide.
So, what we will do then, we will just 1 minute. So, I have shown you this thing and that this is possible, and now we want to find out what will be the principal components given a data matrix X, how to extract the components. Fine. So, here before going to this extraction part, I have to tell little bit of that we are saying that in general we are saying Zj is Aj transpose X, where Zj is the jth principal component, this is jth PC, and this Aj and X, what are those Aj and X? You will be X, you know what is this Aj, we will be defining later on. It is, but if you see the equation, it is similar to like regression coefficients, A11 x1 plus A12 x2 plus A1 p xp, similar to regression coefficient, but it is not. So, now I want to know, I say that variance of Zj you require to compute, because variance of Z1 greater than variance of Z2 like this. What will be the variance of Zj? It will be variance of Aj transpose X, then it will be Aj is the constant here. So, Aj transpose variance of X Aj. As we know, this is a vector basically, Aj is a vector. Later on you will be you know that Aj1 to Ajp, that is the vector. Now, what is the variance of X? X is, what is the variance of X means, that will be the covariance of X. So, covariance of X will be sigma. You have seen earlier in different class, sigma 1 2, sigma 1 p, sigma 1 2, sigma 2 2, sigma 2 p, that is sigma 1 p, sigma 2 p, sigma p p. So, that means this will be Aj transpose sigma Aj. Okay. Then what will be the expected value of Zj? Expected value of Zj will be expected value of Aj transpose X, which is Aj transpose expected value of X, which is Aj transpose mu, because we said that X is p variable vector and it has p mean vector mu 1 to mu p, correct. So, that means essentially that Aj transpose X, which is something which is having Aj transpose mu, Aj transpose sigma Aj, that is the mean and variance part. Okay. So, if they are normally distributed, then you will put normal n. So, Aj transpose is 1 cross p. Now, what will be your mu part? Suppose this one, if you want to do 1 cross p into p cross 1. So, 1 into 1, okay. And this one also will be 1 into p, p into p, 1 into p, that is 1 into 1. So, this Aj transpose X this one will give you a univariate case, because linear transformation of variable x. So, all the principal components are linear transformation, okay, that AJ transpose x, that is the linear transformation. Okay. Now, if you do not get the values of sigma, capital sigma as well as the mu, because these are population parameter, that is mu and sigma. If you know mu and sigma and then given a data matrix you go for this type of that extraction of Zj, then this will be known as population PCA. Getting me what I mean to say? If you know mu and sigma of the population, that x variable case, then you are doing population principal component analysis, but it is seldom known. You will not get these two values. So, what is the then the rescue? Rescue is you will use x bar as estimate of mu and S as estimate of sigma. So, when we use S, actually here we will be playing with the covariance matrix. So, if you use S, capital S, which is the covariance sample covariance matrix, then your principal component analysis will be known as sample principal component analysis. So, we will be writing this as sample PCA, and essentially population PCA is not possible. So, we will go for sample PCA, because when you are talking about applied principal component analysis, then we have to rely on the data and we will go by sample PCA. So, next we will discuss sample PCA, that means how we will extract all those things. Okay. When we use sample PCA, then your expected value of Zj will be expected value of AJ transpose x. Okay. So, this will be AJ transpose expected value of x, which will be AJ transpose x bar, okay, from sample point of view. Similarly, your variance of Zj, this will be your variance of AJ transpose x, which will be nothing but your AJ transpose covariance of x AJ. This is AJ transpose. Now, covariance of S will be replaced by capital S AJ. Correct. So, if I say that okay, this can be normally distributed, then AJX, it is normally distributed with AJ transpose x bar, AJ transpose S AJ. Okay. Now, I will explain you when we extract PC, what are the principles we follow. Getting me? We will discuss the principles now. Now, let us see the slide. Each PC is a linear combination of x1, linear combination of x, a p cross 1 variable vector, that is AJ transpose x. You have seen this one already. First PC is A1 transpose x subjected to A1 transpose A1 equal to 1, that also we have described, that maximizes variability of this variance of A1 transpose x. Second PC is A2 transpose x, that maximizes variability of A2 transpose x and subjected to A2 transpose A2 equal to 1 and covariance of A1 transpose X, A2 transpose X equal to 0. Keep in mind this one. What is happening? We are saying first component you are extracting, that is our Z1 is the first component, which is A1 transpose X. You will extract in such a manner that the variability of Z1 will be the maximum, and also A1 transpose A1 equal to 1, that is the normalization case. So, I have a data set, so and in this, suppose this is my total variability portion. So, Z1 will extract as max as possible by Z1. So, let Z1 variability extracted is this much. Then I am coming to the second PC, which is my A2 transpose X. Here what happened, the remaining variance, I want to extract maximum of the remaining variance. So, variance of Z2, that is the maximum of the remaining. So, let I am able to extract this one Z2. See, ultimately if this is my total variability, Z1 and Z2 has already maybe around 70% is extracted by the two components. There are P components. Okay. This is also here A2 transpose A2 equal to 1 and covariance of A1 x A2 x this equal to 0, because orthogonal components. Now, in this manner, if you go for Zj, then you will write Aj transpose X. Here you will definitely maximize the remaining variance. Already J minus 1 components are extracted, the remaining maximize this one, the remaining variance, and here also you will write Aj transpose Aj this equal to 1 and covariance of Ajx Akx this equal to 0 for k less than j. Why k less than j? What I am saying, you are means k up to k can be 1 to j minus 1. So, when you are extracting this, please keep in mind this is the principles. What I am saying, that when you are extracting the first component, that basically takes care of the maximum variance of the data set subject to this normalization. Then Z2 second principal component goes for the second max of variability of the remaining variance, and subject to this as well as covariance component between the first two, that will be 0. When you go for the third, there also you will maximize the variability of that component subject to the remaining variability, and you also make a normalize it, that A3 transpose A3 equal to 1 and covariance between A3 A1 as well as A3 A2, that X is common, that will be 0. So, in the same manner you will extract. Okay. So, then essentially what we are doing now, actually if I go by the general component, that is Zj, this is my Aj transpose X. We want to maximize the variability of this, which is our Aj transpose S Aj. Now, I am using sample covariance matrix, and subject to what we are saying, that Aj transpose Aj this equal to 1, correct. So, we have two things, first one we want to maximize this, second and we have this constant. So, this second one I can write like this, Aj transpose Aj minus 1 equal to 0. As we want to maximize this with respect to this condition, so what we can do, we can create a function. suppose this function is L, which is Aj transpose S Aj minus lambda into Aj transpose Aj minus 1. Correct? So, we are using a function, this is the Lagrange, L lambda is the Lagrange multiplier. Lambda is Lagrange multiplier. So, you know that this is the general way of maximization process using Lagrange multiplier. So, what you require to do now? You require to find out the Aj value in such a manner that this function will be maximized. So, that means what I want del A by del Aj, that is what I want, getting me. So, this you want to put it 0, provided del to L by del Aj, that will be that matrix you will also get, and it should be the maximization that positive definite and negative definite case is there. So, that condition must satisfy. So, this ultimately results into this equation. It will be like this: S minus lambda I into Aj equal to 0. See, this is, if you take derivative with respect to Aj, it will be 2s Aj. If you take derivative with respect to Aj, it will be 2 lambda Aj, this derivative. So, ultimately it will be 2s Aj minus 2 lambda Aj, that equal to 0. So, 2 will be cancelled out, that 0 is there. So, S minus lambda, but S is a matrix, lambda is a scalar, this into Aj equal to 0. So, that is the equation. Okay. So, now S is your P cross P matrix, because P variables are there, lambda is a scalar, it all depends on that what will be the number of lambdas, but I definitely it will be P cross P matrix. Okay. Then this equation is a famous equation in matrix algebra. So, you will find out that set of linear equations case, suppose, and more famous one is this one. Suppose I want to know the lambda values, then what you require to do, you have to find out the characteristics equation, this equal to 0. So, determinant of this equal to S minus lambda I equal to 0, determinant of this equal to 0, this is a characteristic equation. Getting me? So, if S is P cross P, then this equation has P roots. That means, you will be getting lambda 1 with the condition greater than equal to lambda 2 like this, lambda P. Okay. So, let us see now some more slides here. So, I said that this will be that pth order polynomial is there, P roots you are getting, and you have to, this is the if you know lambda, so basically from this equation you will be able to find out the lambda values. Now, take 1 lambda, put into this equation, and then you find out the A values. Okay. And I will show you one data set now. This is the data set, what is the profit and loss for the example we have started with, and if you plot the scattered, what you are getting that it is almost linear relationship. So, that means one here data reduction is very much possible. So, we tried with two variable case, and what we found out that these are the things. So, first is the covariance matrix. Covariance matrix is S. So, with this example, S is 1.15, 5.76, then your 5.76, 29.54. Now, what we want? We want S minus lambda I determinant equal to 0. So, your I will be 2 by 2, 1 0 0 1, I is identity matrix. So, if I do like this minus lambda I, so that means instead of lambda I am writing 1 0 0 1. Okay, this total determinant if I write, and if I put into 0, so then what is the resultant in this one? 1.15 minus lambda 5.76, then 5.76 29.54 minus lambda, this equal to 0, determinant of this equal to 0. So, ultimately you will be finding out 1.15 minus lambda into 29.54 minus lambda minus 5.76 square equal to 0. It will be it is a quadratic equation of lambda, because our S is 2 cross 2. So, there will be two roots. So, lambda 1 and lambda 2. So, the two roots will be the two roots of lambda, let it be lambda 1 and lambda 2. Now, using this equation you can find out. So, what I mean to say, the resultant equation is 1.15 into 29.54 minus 1.15 lambda minus 29.54 lambda plus lambda square minus 5.76 square equal to 0. So, lambda square minus, you add these two, 9, 6, 30, I think 30 point this lambda, this one, then these two is to be added, that you will be getting some value, this 29, this will be some positive value you will be getting. Okay. If I consider this as C, then your lambda is minus B is 30.69 minus B plus minus root over B square minus 4 AC, A is 1, C by 2 into A is 1. This will give you the eigenvalues, two values, lambda 1 will be your 30.66 and lambda 2 will be 0.03. Correct. So, you are getting your lambda 1 and lambda 2. Then what you require to find out? You require to find out the A values. So, what you will do now? We know S minus lambda I A j, that will be equal to 0. Okay. So, here we will be using lambda j now. So, as lambda 1 equal to 30.66, so you put S is 1.15, 5.76, then 5.76, 29.54, this minus lambda is your 30.66 and into this matrix 1 0 0 1. Okay. This matrix, this into A1 equal to 0. Now, your A1 will be what? A11, A12. Because there are two variables, so I can write A11, A12. A11, A12, that will be 0, this value will be 0, but what will happen ultimately? You will be getting two equation and you will not get unique solution, you will be getting infinite solution under these conditions. Because this equation is 0, this equation is 0, any value, any, so that means there will be infinite number of this A1. So, in order to restrict that, what we will do, A1 transpose A1 equal to 1. So, if A1 transpose A1 equal to 1, then what will happen, A11, A12, A11, A12, that is 1. So, A11 square plus A12 square equal to 1. So, whatever equation you are getting here, that earlier equation, you put A11 equal to, when from this equation what is the value you are getting, you will be getting positive and negative values. So, you put this one. Once you put into this equation for A11, now A12 will be replaced by A11 for from this first equation. A1 is already there and our one relation you will be getting from here, from this you will be getting, because this is 2 by 2, this into this plus this into this. So, it is a two variable equation will be like this, some value into A11 plus some value into A12, that will be 0, like this. So, similarly, now you are getting one relation from here, suppose this is your P and this is your Q, then you are getting A11 equal to Q by P minus A12. Here you put, instead of A11 you put minus Q by P square A12 plus A12 square plus A12 square equal to 1. You will be getting A12 and putting here you will be getting A11. Similarly, A21 and A22 you will be getting. Okay. So, the final one, this is the, that is why this is your A11, A12, this is A21, A22, and you are getting this principal component Z1 and Z2. Okay. This is the manner of extraction of principal component.